So far we've been dealing with position, velocity, and acceleration all along one axis. That is like we're just moving along a straight line. And but of course, motion in real life, quite often will happen in 2 or 3 dimensions. And today we're going to talk about the motion of objects moving through 2-dimensional space. And of course, this is quite common. I mean, here's what we're thinking about. Imagine here's a plane and somebody has a potato cannon or something. Highly illegal. Don't ever shoot a potato cannon. But anyway, you shoot a potato cannon and out comes the potato and it goes up and then, it comes back down. And notice that this motion, this kind of motion, happens in a plane. Okay, and so we're going to call this, the x direction, and this the y direction. And now we really are dealing with, an x and y axis where they're both spatial axes. They're, that we're both identifying a position in space. So if we want to understand the flight of this potato cannon, we need to understand how to describe its position as a function of time, and we need to be able to describe its velocity as a function of time, and also its acceleration. We're going to do the same, 3 quantities, and you could even extend this to jerk if you want, the rate of change of acceleration. But actually, most of the problems we're going to do, we're going to assume the acceleration is constant, and we'll get to that at the end. So the first thing we did in 1D motion was we described the position of objects. And so, and of course that was just, here we just had motion that was just along the x-axis, so we would describe the position as, like x initial equals, 3 meters or something like that. But that's not good enough anymore because now our object might be located up here where it's got an x and a y component to its position. So, that's what we're going to do, and that's what we did kind of in Chapter 3 in describing vectors in 2 and 3 dimensions. So let's redraw my axes here. So here's my object in space. So let's say there's my object, and I can identify that object in 2 ways. I can use polar coordinates, or I can use rectangular coordinates. And the ones you use, which ones do you use? Well, it depends on what the problem asks for. Whenever you hear them say, what is the magnitude and direction of blah, 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 well, magnitude and direction is polar coordinates, right? But if they don't say otherwise, unless they say give the magnitude and direction, you can leave a vector in rectangular coordinates. I mean, that's what most of us do. Yes?
When it asks for the magnitude and direction, I've been putting 2 separate answers. Is it okay if I just put it as a coordinate?
Yes.
Okay.
Yes, 2 coordinates, yes. So, now, so here's my object located in space at a particular instant in time. So this is now its position vector. Now remember what we said about position. What is the operational definition of position? Position is where an object is located in space with respect to the origin. So this arrow, this position arrow, will always start at the origin and extend out to where our object is located. That's by definition of position. But let's suppose this object is actually moving in space. Well, first, let me describe that position. We're going to give it a little r vector, and that's usually what we use is a little r to represent some position vector. Remember, we used x or y, in Chapter 2, but that's not good enough anymore. So what R represents is where that object is actually in three-dimensional space. We use R as well to represent it. And so R, now let's say that this is where the object was initially. So I'm going to call that R initial. So R initial has a, well, it has an X component and a Y component, doesn't it? So Rx initial, and then plus Ry initial. And now you can, this is where people who aren't studying physics, you know, and they look at the work you're doing, and they'll look at something like this, and it just looks crazy. Okay, so I don't know, but it's really a language, okay, that we're using, and so if you know what the symbols mean, this actually means something very simple. Here's my initial position vector. It's a vector. That's what that little arrow means. It's my initial position. That's, you know, meaning where I started from. So it's got the little I subscript for initial. And because it's a two-dimensional vector, it's got a component in the x direction, which we also indicate. This is a little bit redundant, isn't it? Because I've got the x subscript here, and I also have the I hat unit vector. And remember, the I hat unit vector just means, hey, this stuff, it's in the x direction. That's all it means. That's all I hat means. Hey, it's in the x direction. So don't freak out when you see a unit vector. It's just telling you what direction the stuff is that's in front of it. Plus, you know, R, Y, you know, in the, well, what does J hat mean? It means in the Y direction. That's all it means. It has no units associated with it. It doesn't change the magnitude. It just says, hey, go in this direction. That's all it means. Okay, well, suppose this object is moving. And so you look in a little while later and you notice the object has moved over here. And so here is the object's final position. So this is R final. And so R final is equal to Rx final plus Ry final in the j hat direction. So this just identifies the two vectors here. And of course, if I'm doing an actual problem, you know, a concrete problem, they're going to put numbers in here in meters, right, or centimeters, or whatever units of length you're using, because these are position vectors. Now, obviously, the object changed its position. Now, remember when we were dealing with just the x-axis, if I started here and ended up here, if this was x final, let's say it was 5 meters in my example up here, well, then, you know, delta x was right here. We said delta x was my change in position, my displacement, and it started here and went here. So you'd say, oh, 5 meters minus 3 meters, that it gives me a displacement of 2 meters. But notice that my displacement vector started at my initial position and ended at my final position. And that's what we're going to do in two-dimension and three-dimensional space. The change vector, the change in position vector, or the displacement vector, starts here and goes here. So there, and we call that my displacement vector. Of course, instead of delta x, what vector am I changing? I'm changing the r vector, so this is delta r. Now, let's take a look at delta r. Well, if I were to draw the components for it, it's got an x component and a y component. And I treat those components different, you know, it's just separately. Now, how do I get, well, this is the delta x, and this is the delta y of my displacement vector. So in other words, just generally, I can say, well, delta r is going to be equal to some delta x and some delta y. Okay? Makes sense to everybody? I think if you look at the picture, it's very clear. Oh, we changed in x, and we changed in y. And so you say, okay, well, look at this this is delta x, but this delta x, obviously delta x is going to be in the x direction. And obviously delta y is going to be in the y direction. So why do we need the I hat and the j hat? Because these are going to be numbers. They're not, like 5 meters. And you need some way of indicating what direction that 5 meters is in. Okay, so there you go. All right, so obviously, delta r here is r final x minus r initial x. This is x. Oh, I kind of messed that up. I was going to leave it. The final x position minus the initial x position gives me my delta x. And then plus, r y final minus r y initial in the y direction. Of course I can extend this to the z direction if I wanted to do all that writing, okay, but I don't. Okay. How you guys doing? This is pretty easy, I think. I hesitate to say that because, oh, this is pretty easy, right? And then, because somebody who's struggling will say, oh gosh, if I ask a question now, I really look stupid. So, it is easy, but it's easy to get stuck. So if you're having a moment of stuckiness, please don't hesitate to ask questions. All right, so here we are. Now, it took time to do this, didn't it? It took time. And so if we divide the time, divide the displacement by the time, we get average velocity. So now we have, I'm going to subscript it like that, average velocity. Well, that's going to be equal. By definition, it's equal now to delta r over delta t. But here's the critical idea. Notice that I'm doing exactly what I did when I was dealing with one-dimensional, position, velocity, and acceleration vectors. Except I'm now doing I'm doing two of them at the same time. I'm doing the x direction and the y direction at the same time. But just treating them separately, but they're still there. So if I take this and plug it in over here, I have, this is delta x over delta t in the I hat direction, plus delta y over delta t in the j hat direction. See, I'm changing my position in x and y at the same time. That's kind of what defines two-dimensional motion. Well, this is my average velocity. I mean, what did we do for instantaneous velocity? Instantaneous is just the average without the AV subscript there. Okay, so we'll take the limit as delta t goes to 0 of delta r over delta t. Now, this is obviously, right, a derivative. So the instantaneous velocity here is dr dt. Okay? And what I'm going to do now is take this derivative operator and work it on here and here, on this and this. And when I do, I get dx dt in the I hat direction plus dy dt in the j hat direction. And of course, this makes complete sense really what is this? The velocity, what is dx dt? Well, that's the x component of my velocity vector. If I was to draw a velocity vector, this is just the x component of it. So this is just Vx. Okay? So again, I'm not doing anything differently than I did before. I'm just doing it in the x direction and the y direction at the same time. So it becomes a little cumbersome. You have to, show more work. Well, what if your velocity vector is changing? What if, and let me show that right here. What if I've got some object that's here's y and x, and I'm going to draw the path of some object. Maybe the object is, moving along some path like this, and obviously this is not a function, is it? But we could describe it with what are called parametric equations, right? The x is a function of t, and the y is a function of t, where time becomes our parameter. Have you done parametric equations in your? I think you did them. I know we did them when I taught AMA, but that was a long time ago. But anyway, like let's say the object is right here, and it has a velocity vector that looks like this, right? The velocity vector tells you how fast you're going and in what direction. And then, but maybe when they were over here, so maybe this is like v final, but maybe over here they were moving like this. Maybe they're moving a little faster. Well, between here and here, there was a change in velocity. There was an acceleration. And so, both in terms of speed and direction. And so, we can have a, if I were to pick these up and hook them up head to, tail to tail, because I'm not adding them, it's, well, here's V initial plus delta V. There's my delta V vector right here, from here down to here. There's delta V. So I didn't draw this very well. Here's my final velocity. Here was my initial velocity. When I remember that delta V. Here's one way to look at it. Delta V, right? That's defined to be, whenever you have a delta, it's just the final minus the initial, right? Whenever you have a delta. But this is a vector equation. So, so you have to think in terms of, adding and subtracting vectors. Well, I can rearrange this. I can solve this for V final. The final velocity is just equal to the initial velocity plus how much I changed my velocity. I mean, this makes total sense all by itself, right? Here's how fast I'm going. Well, here's how fast I was going plus how much I changed how fast I'm going. Okay? Except, of course, these include, when I say how fast I'm going, I include the direction in there. It's a velocity vector. So, if this is my final velocity over here, I say, okay, my initial velocity plus my delta V gives me my final velocity. Okay, in any case, how did we, we're still going to use this right here. How did we define average acceleration? So, the average acceleration, well, all we're going to do is we're going to say, look, the average is just the change in velocity over the change in time. Okay, and so this is going to be V final minus V initial. over whatever change in time you had. And now these vectors, you know, have their x and y components, and we can extend those components to look like this. And I think this is going to be pretty clear. Well, the final velocity, what is it? The final velocity is Vx final in the I hat direction plus Vy final in the j hat direction. I mean, this is V final. Then we have to subtract this. Well, what is this? This is Vx initial. Am I still on screen? Yeah. Vx initial. Oh, I didn't need to put. You can put it. It's not bad. I didn't need to put those vector hats on it there. And then in the I hat direction minus Vy initial in the j hat direction. So this is a mess, isn't it? Okay. But you see, we do have common terms here, and you can think of the unit vectors as being a factor, okay, and where I can only, you know, add or subtract, you know, common factors. So look at this. I got Vx final. I got Vx initial here. Those I can subtract. So if I go Vx final minus Vx initial, I get delta Vx. And then when I do this, I get my plus delta Vy. And of course, this is all divided by delta t to get my average acceleration. Okay, and then we can just distribute this delta t separately. And again, this is exactly what I did for one-dimensional motion, but now you're saying that, okay, I'm just separating it in the x direction and y direction. I'm treating them completely separately. And so A, the average, is going to be equal to, well, actually, I don't need to go any farther than this, right? This is it right here. This is my average acceleration equation. Now, what do we do to get instantaneous acceleration? Take the limit as delta t goes to 0 of this whole mess. And I'll just put delta v, just to save writing, over delta t. So, but when I operate this derivative on here, I can say, oh, okay, I've got an ax. I've got, this is the x component of the acceleration. This is the y component of the acceleration. And I can move on from there. So, really, all you need to know for two-dimensional motion is that all the techniques that we used in Chapter 2 for one-dimensional motion apply. They just apply to the x direction and the y direction, and eventually in the z direction, you're just doing the same thing, but you're doing them at the same time, which means it's more work. You've got to worry about the x-axis and the y-axis. Okay. And so you'll work some problems doing that. Now, the last thing I want to talk about is, see, nothing in here assumes that the acceleration is constant. This can be a function of time, and this can be a function of time, right? And if those are functions of time, then the velocity vectors are functions in time. And obviously the position vectors are functions in time. Yes?
The changing velocity vector for like what direction? Changing velocity vector.
Okay, now remember this is an average acceleration right here because, well, I didn't draw this very well, and actually we're kind of anticipating what we're going to do when we do circular motion, but it would be in my drawing right here. Let me zoom in so I don't have to redraw it. Okay, so the question is, what direction is my acceleration vector in? Is that what you're asking? Or the change in velocity vector?
Yeah.
Well, you can see here, that's, now just qualitatively, okay, here's my initial velocity. I moved over. Well, let me just redraw it. Here's the initial velocity that I drew, right? Let me just pick it up and make it a little bit bigger. There's the initial velocity. And here's the final velocities right here. Now, watch what I do here. Maybe that's V final. Now, what is delta V? Well, delta V is V final minus V initial, but if you rearrange this, you can get a different vector equation that V final is equal to V initial plus delta V. Well, when this vector plus this vector equals this one. So here's V initial. V initial plus delta V has to be equal to this. So you just draw a line connecting them. And see that arrow I'm drawing? That's delta V. So what is the direction of delta V? Well, in my little picture here, it's down and a little bit to the right. Now, obviously, if you're doing all this with numbers, you'll have, for delta V, you'll have an x component and a y component, and you'll be able to use the Pythagorean theorem to get the magnitude and inverse tangent, as we did with all vectors, in chapter 3, to get the angle with respect to the positive x-axis. Does that answer your question? Okay. Well, if we assume that the acceleration is a constant, let's assume that we have a constant acceleration. Well, that means the x and y components are constant. If a is a constant, that means ax is a constant, and ay is a constant. Oh, heck, az is a constant. We haven't done that yet, but no reason not to. Okay? This means that I can use the kinematic equations in the x direction, the y direction, and the z direction. Now, what were the kinematic equations? Well, in the x direction, well, first of all, we have v equals v naught plus at. But now, look, we're dealing with components. So, we're dealing with x, y, and z directions. So if you're looking at the x direction, you'll want to go v final x, v naught x, acceleration x. So you just want to put a subscript, an x subscript on everything. What if you're dealing with the y direction? Oh, okay, well, vy equals v naught y plus ay times t. Okay, now what about the z direction? Well, of course, we'll do the same thing. If I've got room, I'll just stick it up here. V sub z is equal to v naught z plus az t. Okay. So, look, these are probably all going to be different. And the acceleration and the x and the y and the z, those components of acceleration are going to be different. But what is the same in all three equations? What? Well, okay, no. What? Yes, the acceleration is constant with time, but the components aren't the same. So what the structures are the same. What quantity is the same in all three? Time is going by in the x direction, in the y direction, in the z direction. Yeah, you got these different directions, but time is going by. So this motion, this part of an object, remember you have one object that's moving, okay, and it's being accelerated in some bizarre direction. Okay, but this is describing the x component of its motion, the y component of its motion, the z component of its motion, and they're all three of these motions are happening at the same time, right? It has to, or the object would split apart somehow. So the key idea when you're working an example problem is to work the problem as best you can. And now, I don't think you're going to work the z direction in the homework at all. It's all going to be x and y. So let's just ignore the z direction for now. What you have to do is work the problem in the x direction and y direction separately. Treat them as two separate problems. But what's the link between here and here? It's time. Whoops, why did I do that? Time. Time is the link. So problem-solving strategy. Use given, find, and solve. But split up the x and y components of what's given. Then apply the kinematic equations to the x direction and the y direction separately. But look at what you're given. And you can, if you can solve for time, you can use them on both sides. And you can almost always solve whatever you're looking for whatever you're looking for. So that, I think, is enough for now. We will work an example problem. I think we'll have a little bit of time in class to do that. So that is all.